Any ideas? What do you think? Yes, sir.
X over 360 times Y.
Okay. Okay. How about that? Now we know that if I want to get the area of this sector, it's just going to be some fraction of the whole, right? So the fraction of the whole, the suggestion is it's going to be x over the whole angle. Now it's exactly right, except do we want to use 360 there? 2 pi is what we want to use. Okay, and let me just say something about that. At this point, to you, I can see where radians and degrees are probably just interchangeable. It's like meters versus feet kind of a thing, right? It's not that way. Degrees are completely arbitrary. There is no reason that a circle has 360 degrees other than the fact that 360 is a highly divisible number. That's it. There's no other reason. People, whoever, I don't know who it was that came up with the first, yeah, that's true. There's no reason why 360 is important. It could have just as easily been, when that was first invented, I don't know who came up with that idea. I really don't know who the mathematician was that decided it was 360. It could have just as easily been 180 degrees in a circle or 1,000 degrees in a circle. There's no reason it's 360. 360 is just a number that was grabbed out of the air, arbitrary.
Really?
Okay, really?
Just picked a number?
Just picked a number. Yeah.
They could have picked any number.
Could have picked any number. The reason they picked 360, like I say, the reason they picked 360 is because you can divide it up into, if we divide it into fourths, we get 90 degrees. Divide it into eighths, we get 45. It's highly divisible. So when we divide it into fractions, we get lots of integers. And so that's why it's a good number to pick. We wouldn't want to pick like 113 or something like that. But really, that number is totally arbitrary and capricious, and for that reason, you got to believe that it really is pretty meaningless, right? 360, it doesn't mean much. 2 pi, however, means a lot. 2 pi is an inconvenient number. It's an irrational number, right? I mean, we can't write it as a decimal. So right there, you get the fact that 2 pi, why would we pick something so difficult when we could pick something nice like 360? Because 2 pi is real. 2 pi actually means something. Here's what it means. I digress, and this is interesting. Okay, first of all, somebody tell me, what is the definition of pi? And right away you start to think, when we answer this question,
Circumference divided by diameter.
there you go. Okay, pi is a universal and possibly even a super universal constant. I'll talk more about that. Maybe on Friday if I have time we'll talk about parallel universals a little bit. So pi is a number that arguably any intelligence in a universe with any physical dimensionality would come up with, because in any flat space, in any two-dimensional space, if you take a circle, it's always, regardless of the size of the circle, regardless of the number of time variables, the number of temporal constants, doesn't matter. It's always going to end up being the same thing. It's just the ratio of the circumference to the diameter of a circle, right? And so already we can see, almost philosophically, that pi is probably a pretty good candidate. If we had to come up with some kind of a number that's going to describe the angle in a circle subtended by arc or something in a circle, that pi is probably a pretty good candidate for that. And it is. Okay. So if we look on a circle, we know that the circumference of a circle is 2 pi r, right? So if we happen to choose a unit circle, a circle with radius 1, then what's the circumference? If the circumference of a circle is 2 pi r, it's 2 pi. Oh, wow. Okay, so 2 pi is actually not necessarily a measure of angle. What it really is a measure of arc along the unit circle. But that's easily translatable into an angle, isn't it? Right? Because each point on the circle, if an ant starts here, walks in that direction and stops there, he has described a certain angle around the edge of the circle, right? And so pi really means something. When we say something like 2 pi radians, it's got an intrinsic meaning that can't be different. It's talking about how far you're traveling around the length of arc you're walking through on a unit circle. Does that make sense?
Mm-hmm.
okay? So, incidentally, how many of you guys are in physics? Hopefully a lot. Okay, here's something you gotta know about. This is a biggie. I'm sure this will come up in your physics class, but my background's in physics. When you're dealing with kinematics in physics, which you'll get to, not, you're probably maybe starting it now. When you talk about angular motion versus linear motion, linear motion, we're just talking about linear displacement or velocity or acceleration. Angular motion, you're talking about motion around a circle, right, if that's the center. We've got angular displacement, that's the angular equivalent of displacement, how far, what angle you can move through rotationally. Angular velocity, measured in rate of change of angle, and then you got angular acceleration. You can deal with each of those independently exactly the same way. What you're going to find is the rules of kinematics in linear land work the same as the rules in angle bending. They're almost mirror images. But when you cross over, when you start doing things like you talk about actual movement, talk about actual physical displacement along the edge of a circle, right? So you start to talk about things like centripetal acceleration, or you talk about tangential speed. How fast when you go back to the days of yore when you played on merry-go-rounds, right? When you're on the edge of the merry-go-round, if it was a glass bottom merry-go-round and you look down, you're going through, you're covering the ground pretty quickly. It's just a blur. In the middle, it's no big deal. You're not moving very fast. So when you make that translation from the angular to the translational, you have to, absolutely have to, stick with radians. When you're talking strictly about angular stuff, pick whatever you want. You can use degrees, you can use radians, whatever. When you're talking about linear stuff, obviously you're talking about just meters or feet or something. That's really not up for grabs. But when you cross over, when you're talking about actually displacement along a circular path, or acceleration, say you're talking about centripetal acceleration, what's the force that's pulling you towards the center, things like that, you absolutely have to use radians. You can't use degrees or you'll make a mistake because it doesn't work, okay? That's the most, having taught physics for years and years, that's one of the most common mistakes people make is they think they're interchangeable, and they're not. Remember, when you're mixing the two up, if you're mixing linear measurements and angular measurements, those of you in physics class, you have to use radians. Okay, but back to business. Back to my class. Okay, so then we can come up with the area of the sector pretty easily. I guess we never finished, did we? Did I start writing that down somewhere? Maybe I did. Well, let's do that. Okay, so the area of the sector, the red sector then, is just going to equal x, which was our angle, divided by 2 pi, right? Does that make sense? That's the fraction of the whole pi. Whole pi is 2 pi, and then we just had x degrees, times the area of a circle, right? Which was just pi times 1 squared in this case. So pi. So what happens? What's our area equal to then? That's just 1. The pi's cancel. Just x over 2. Yeah. Okay. So we got all 3 areas now, right? We got the green area, we got the blue area, and we got the red area. Okay, what are we going to do with that? We could put those in order, right? Wouldn't you agree that the blue's the biggest, the red's in between, and the green's the smallest?
Yeah.
Okay, so this is getting too messy. Let's go to a new page.
That's it. That's it.
This is a really cool proof. You're going to like this. Okay, so we could say then, so we had tangent x over 2 is greater than, we had theta over 2 was the red. That was in the middle. And then the smallest was sine theta over 2. Okay, let's just do a little algebra here. Let's multiply each of these through by, or let's divide each of these through by 2 over sine theta. Multiply by 2 over sine theta. So why am I doing that? Well, first of all, let's rewrite this. This is just sine theta over 2 cosine theta, right? This one stays the same, that's just theta over 2. And this one, sine theta over 2. So if I multiply each of those through by 2 over sine theta, watch what happens. Well, I get some cancellation. All right, the sine thetas cancel, the 2's cancel. Here, everything cancels, so I just get a 1. Right here, the 2's cancel. And I end up then with, what am I left with here? All I've got is 1 over cosine theta, sure. 1 over cosine theta is greater than, here I got theta over sine theta. And here, whoops, here I got 1. Okay. One last thing we're going to do, we're going to invert all these if I flip them over. Okay, but what do you suppose happens if I have an ordered relationship among fractions and I flip the fractions? So this is, we can see what's going to happen to the individual terms. This one's just going to become cosine theta, right? Oops. That's cosine theta. This one's just going to become, oh, I somewhere along the line I put in thetas instead of x's, sorry. Yeah, remember that? Sorry, if that's confusing. I should have put in thetas from the very beginning. We had an x for our angle, but way back in our picture, here's all I did. I'm sorry about that. I just turned that into a theta. Okay? Make sense? Were you wondering where that came from? Is that confusing?
I got it. Genius.
Sorry about that. And really, that was kind of a dumb move on my part. X is usually not an angular variable. Theta is usually what we use. Theta or alpha or phi or things like that for angles. So I should have probably used theta from the beginning. I should have known I was going to do something like that. But you can make those X's in your notes if you want to. That's fine. And then this is just a plain old 1, right? But what's going to happen to the inequality signs? That's what I'm getting at. Oh, they're going to flip, aren't they? They're going to flip. Now, you can prove this to yourself inductively pretty easily by just taking a couple examples. Right, if I had something like 3/4 is greater than 2/3, when I flip those, what's going to happen? Well, I'm going to get 4/3 and 3/2. And 3/2 is, see what I'm saying? It's going to have to flip around, isn't it? So yeah, all these signs get flipped. That guy's going to go that way. That guy's going to go that way. Okay, now, this comes down to that little sandwich theorem that I drew for you, and you probably forgot about. We didn't do anything with it.
Dude, I got it. I'm all over that.
Okay, go back a ways, don't we?
Oh,
It's
goodness.
fun watching that cube go anywhere. So here's
So many sides.
here's our sandwich theorem, or the squeeze theorem, whatever you want to call it. Interchangeable names. What this told us, remember, is that if I have some ceiling function, say the orange function, h of x, some floor function, the green function, f of x, and some function that's trapped in between, if the limits of the top and bottom functions, as x approaches some value, converge, then they're going to squeeze that middle one to the same limit. Right? Make sense? Okay, so how does that apply here? Well, let's take a limit. Let's take the limit as theta or x, whatever you're calling it, goes to 0, and see what happens to each of these 3 cases. Okay, so what if we take limits of each of those, right? What is the limit of, and rather than rewrite this whole thing, we're just going to take limits as x approaches, or theta approaches 0, right? As theta approaches 0, what is the value of cosine approach? What's cosine of 0? 1, right? So the limit of cosine theta as theta approaches 0 is 1. What's the limit of 1 as theta approaches 0? 1, right? And so therefore, this indeterminate form that looks like 0 over 0, right? That's what motivated this whole thing, you might remember from a couple days ago, is when we take the limit of sine x over x or sine theta over theta, whatever you want to call it, as theta approaches 0 or x approaches 0, it looks like by direct evaluation we get 0 over 0, so that's more work. But we just proved that the limit is actually what? 1. Yeah, it's actually 1. And so we got our special limit. There it is. The limit of sine theta over theta as theta approaches 0 is 1. Okay, so we can use that to our great advantage. What if we end up with something like this? Okay, what if you get one like that? I want to try direct evaluation, right? But if I plug in 0 for x, what's tangent of 0? 0, yeah. So I get 0 over 0, right? So that's indeterminate. Now, the more work associated with this one is using trig identities to rewrite this so that we can get this special limit popping out. Okay, so what do you suppose we're going to do here? What do you suggest we do? If we're faced with a tangent, what does that just probably screaming out? We got a tangent. Yeah, okay, we want to write the composite trig functions. The tangents, the cotangents, the secants, and the cosecants in terms of the primitives, right? The fundamentals, the sines and the cosines. So the first thing we want to do is take that tangent and turn it into a sine over cosine. So this becomes limit of, I'm just going to pull that x out, how about? And we'll make this tangent a sine x over cosine x squared, right? And you got to remember one thing also, you're dealing with trig functions. When I use this notation, when I put the exponent seemingly between the function and the argument in the angle, what is that really saying? What is tangent squared x actually say? Okay, good. What it's really saying is the quantity tangent x squared. It's just it saves us some writing, right? But you always got to at least think of it that way. Okay, so now what? Still 0 over 0, but I can regroup this, right? I've got these factors. We know that multiplication is commutative and associative, so I can mix those things around and group them in any way I want to, right? So how am I going to do that? I've got a sine times a sine on the top. This stuff is really kind of tricky when you're first looking at it because it just seems like it's a bunch of disconnected algebra. But as much as you can, I think what separates really good calculus students from just plain old good calculus students is being able to kind of see strategically, what am I trying to eliminate? Right? I'm trying to eliminate a factor of x from the top or the bottom, right? I want, at some point, when I take my limit, I want either the top or the bottom to give me an answer back that's not 0. So I'm not stuck with that 0 over 0 more work issue, right? Okay, on the bottom, what's the one that's causing the indeterminacy? Where's the 0 coming from? That x. If I could somehow absorb that x into something else and get rid of it, right? We'd be set. Now on the top, I've actually got two factors that are going to 0. I've got the sine x times the sine x, right? Does that make sense? So somehow I got to try to whittle that thing out of there. Any suggestions? How could I, if I write this in terms of just all the individual factors, maybe this helps, at least to think about it this way. On the top, I've got a sine x times the sine x, right? On the bottom, I've got an x times cosine x times a cosine x. Now you don't have to write it that way, but you're thinking about it that way. Can I group those in a way that's going to be helpful than that. Yes, sir.
Isn't the law of sines like sine times cosine equals 1 or something like that?
Well, we got sine squared theta plus cosine squared theta equals 1, and that's a useful one. Doesn't come into play here, but a lot of times it will on these kinds of problems. But if I can group these things, do you see a couple that, I mean, look at this. I know that when I take these limits, and that's all I'm trying to do here is take limits, right? Look at that right there. See? What's the limit of that red bubble? 1. Yeah. So I want to write this as products of separate limits. I've got this one big limit, but I can partition it up into a product of some smaller limits that maybe I can deal with, right? So let's rewrite this then as limit of sine x over x times what's left over. Well, sine x over cosine squared x. See what I'm getting at? And you don't even have to necessarily write them as separate limits. We could if we wanted to. This is fine. We could just write this as limit as x approaches 0, even of just individual factors. I could just say sine x over x times sine x over cosine squared x. They mean the same thing. Because when I take these limits, this is a special limit that we now know, right? That's the one we just proved. Does that make sense? Okay, so in the limit, this limit goes to 1. Right? This limit is one that we can take. As x goes to 0, what is the limit of sine x over cosine squared x? Well, sine x goes to 0, cosine 0 goes to 1. 0 over 1 is just 0, right? And so in the limit, we get 1 times 0 equals 0. Does that make sense? I mean, not completely. It shouldn't make sense completely, but I mean, it's pretty new stuff. But you can get the idea?
Yeah.
Okay. Okay, which now we're leaning on. We're going to run out of time here. This took time. That's okay. It needs to take time. We're leaning on a concept of limits that I had to just look at the theorems, but let me just point something out. In your textbooks, and you don't even need to look in your textbook, I'll just write it down here. These are theorems 1-1 and 1-2. Okay, this is kind of important. If we have something like the limit of f of x plus or minus g of x as x approaches some value, okay, we can break that up into separate limits, right? I can take the limits individually. The limit, now here's how we'd say that. The limit of a sum or difference is equal to the sum or difference of the individual limits. So I could write that as the limit of f of x plus or minus, depending which one it is, the limit of g of x. So I can take out bite-sized pieces, deal with them individually. Okay. Also, the limit of a product, the limit of f of x times g of x as x approaches c is equal to the separate limits. The limit of a product equals the product of the limits. So I can break that up into the limit of f of x as x approaches c times the limit of g of x as x approaches c. Okay? In other words, here's an example. If I have the limit of 2x times sine x as x approaches pi fourths, I don't have to deal with that in one lump sum. I can take like the limit of 2x by itself, right? When I write that, it just says limit. right? I can break it up into separate limits. See how handy that is? You do it in your head anyway, but it's just justifying that. It's saying we can break this up into bite-sized pieces. Okay? Same with the quotient. The limit of a quotient I can break up into the limit of the top separate from the limit of the bottom, right? And why am I stressing that? Because we just did it. We just did it right here, didn't we? We took this big conglomeration of trig functions in x, and we split it up conveniently, right? We split it up into the limit of the sine x over x, which we now know, and then the limit of the rest of the stuff, which is no longer indeterminate. Okay? Sort of, kind of, maybe?
Oh, yeah.
Well, we need to do a little more on that. I'm not done. There's a few more examples I'd like to do. I'll go ahead and put the assignment up. And we'll take maybe, promise you, short time on that tomorrow, and then we'll get to the lab and you can do some work on it. Okay?